last lecture, we discussed about mixing of two gases and we talked about how the free energy changes in the mixing process. And we showed that the associated free energy change in the mixing process is always negative, which means mixing will happen spontaneously. Now we'll be discussing the mixing of two liquids, and we'll be discussing a law which is known as Raoult's law. This is after the French scientist Raoult, who proposed how the free energy will change if we mix two liquids. Now, to begin with, let us consider that we have a sealed container and we have a liquid, say liquid A, and this liquid which is liquid A, so it is in equilibrium with its vapor. So this is when the liquid is in, or the substance is in pure form. It is only one component system. Now suppose we add a second component which we are denoting as B. So right now in the liquid phase we have A plus B, and in the vapor also there is A plus B. So this phase is liquid phase and this phase is liquid phase, and this top portion is vapor phase. So this is a mixture. This is mixture of A and B. Now, just to denote the pressure for, or the vapor pressure for pure A, instead of writing it as PA, we'll write it as PA star. What this star denotes for pure substance. So initially the chemical potential was also, we'll write it in the similar notation. Instead of mu A, we'll write it as mu A star. So before mixing, what we had is mu A was equal to mu A 0 plus RT ln PA by P0. Now this PA is the initial pressure of the gas. So if initial pressure means actually the partial pressure is nothing but equal to the total pressure, P0 as before is taken to be 1 bar. Now since initially the liquid is in pure form, we'll use a star notation here. Now see that mu A0 star it's meaningless, because mu A0 corresponds to the chemical potential of the substance in corresponding to 1 bar of the pressure, so which is the standard state. So we are not writing mu A0 star, so it obviously is equivalent to mu A0. Now think about it. After we mix the solution, or it's not a solution, it's a pure liquid with another liquid B, now it forms a solution or a mixture of two substances. Then we are writing it as a mu A because it's no longer a pure substance, and that mu A will be nothing but mu A 0 plus RT ln PA by P0. Here I'm writing PA, not PA star, and also mu A, not mu A star. But note that the mu A0 will be same because it just corresponds to the standard state in either case. So what Raoult's law says is, if we now compare what is the mu A or the, if we just take the difference between these equations, so let's call it as equation 2 and let's call it as equation 1. If we just take 2 minus 1, then we get mu A minus mu A star, and that mu A star I'm just moving on the right hand side. So it will be mu A is mu A star. These terms cancel with each other, and then we have RT ln PA by P0, and here we have RT ln PA star by P0. So we can take RT common, and it will be just like ln x minus ln y is ln x by y. We can write this as RT ln PA by PA star. Now what is PA? PA is the partial pressure of component A in the mixture. Since it is partial pressure, obviously it corresponds to a mixture. And what is PA star? PA star is the pressure of the same component, or the vapor pressure of the same component, when it is taken in the pure form. Now the mole fraction should be equal to PA by the total pressure, which is nothing but, say, PA plus PB. Now Raoult's made an approximation. He said that this mole fraction we can write as, or we can approximate as, the XA is nothing but PA by PA star. Remember that this is not correct, because actually XA, or the mole fraction, should be equal to the partial pressure in mixture divided by the total pressure. But Raoult approximated that the mole fraction is nothing but the partial pressure divided by the pressure of the liquid, or the vapor pressure of the liquid in its pure form. So this is known as Raoult's law. And using the Raoult's law, if we just rewrite this equation, we'll get mu is equal to mu A star plus RT ln PA by PA star. We will write it as XA. Now some textbook write this as a Raoult's law, but it is not very correct, because this is Raoult's law and this is Raoult's law when applied to for ideal gases. Now the substances which follow this equation, or the solutions which follow this equation, are called as ideal solution. Now let us try to understand why this approximation actually holds. Now think about a situation. Suppose A is a liquid and suppose B is a solute, which is say for example A is water and B is some salt. And then what will happen is that we are trying to give again a molecular level picture. So in the liquid you have all these liquid molecules, suppose, or molecules of A. So these are molecules of A, and suppose I'm writing the molecules of B like this. There are also few molecules of A in the vapor phase. So this was the initial condition, and then from pure A we added salt, where the situation is like this. So we have also some salt molecules here, but usually in the vapor phase we'll still have only molecules of B, molecules of A, because usually the salt is non-volatile. So you can approximate this pressure, which is basically the partial pressure of A here, and which is basically partial pressure, this one was PA star. They will be of course different, I'm coming to that, but then you can approximate the total pressure. In this case it will be equivalent to the liquid's original pressure. Now why we are making that approximation? The reason being, when the solute is present, the evaporation of the solvent molecules into the vapor phase will be little bit suppressed. So definitely PA star and PA will be different. However, the total pressure expression, which is which we took as, instead of PA plus PB, which is the P, and that we approximated as PA star, is not a very bad approximation. The reason being, usually the PA star will correspond to a pressure which is purely contributed by A, and similarly the total pressure here, when suppose the solute also has very few molecules, is also largely contributed by A. So the total pressure can be approximated by PA star itself. So this is the molecular origin for Raoult's law. Now you can actually have a kinetic model to describe this entire process. Remember that at equilibrium, every equilibrium is a dynamic equilibrium, which means there will be some molecules of A going into the vapor phase and some molecule of the B A going into the condensed phase, and the same thing is happening also for the molecules of B, which is a solute but which has very less number in the vapor phase. So what we will have is that PA plus PB, we are approximating it to be PA star, and then we can think that at any particular temperature, the rate of vaporization, that will be proportional to the mole fraction of A, because if you think that it has to be proportional to the mole fraction of A, because it is proportional to the density of A in the mixture. But now instead of the pure density, we have to calculate the mole fraction, because now the solutes are present and they will influence the evaporation of the vaporization of the liquid. So it will be proportional to mole fraction of A, which were the proportionality constant we are suppose writing as K vaporization. Similarly, there will be a rate of condensation, meaning all these A molecules are also coming back, and that rate will be proportional to now the partial pressure of A, because if the partial pressure is high, so there will be higher tendency of the vapor to go back into the liquid. So if that it is proportional to PA, we can also consider some kind of rate constant, which is the condensation. So in equilibrium or at equilibrium, we know that these two rates must be equal. So we can write that XA is nothing but K vaporization divided by K, it will be the other way, it will be K condensation divided by K vaporization times PA. Now if you take a pure form, then for the pure form we could write that XA is 1, and then K condensation by K vaporization is basically this pressure then is nothing but PA star, and then you can easily compare that this ratio of the constants, which is K condensation by K vaporization, is nothing but 1 over PA star. So you can use it in this equation again and eliminate these arbitrary rate constants, and you can easily figure out that PXA will be nothing but PA divided by PA star. And that's what was the essence of Raoult's law. So Raoult's law is originating due to the fact that when I have a solute solvent mixture, then of course some part of the solute may go into the vapor phase, but more than that, the solute also suppresses the vaporization of the solvent. So the vapor pressure of the solvent must change, which means PA must change from PA star. But when you take the total pressure can be approximated as the vapor pressure of the pure solvent. The reason being, usually in the mixture, only a few amount or few trace amount of the solute goes into the vapor phase. So it is largely contributed by the solvent molecules. So we can have this situation. However, uh, there is a problem in if we want to uh, have a solution or have a change. If we want to plot this, how the vapor pressure or how the pressure is actually changing with respect to addition of the solute or the solvent, then we see a very interesting situation. Now for if there are two liquids, sometimes we do not it's not very ideal to call one substance as the solute and the other substance as solvent. So these are just two solvents. Now let us just try to have a look how it looks like in real life. So if one plots the pressure versus the mole fraction of one component, in this case the plot is shown for acetone and carbon disulfide, and we are plotting the mole fraction of carbon disulfide, where actually both are in liquid phase. So it's not a solute solvent system, but it is a solution of two solvents. So you can think that at a very zero concentration of carbon disulfide, when we have a pure acetone, so we have some pressure which corresponds to Pa star of acetone, and then once it we keep on increasing the amount of solute in this case. If we think that it is a kind of solute, this carbon disulfide, if we keep on increasing, and if you watch the expression for Raoult's law, now how the expression for the Raoult's law should look like. Now remember, the Raoult's law is a very much simplification. It just says that Pa will be nothing but Xa into Pa star. So suppose I'm adding Xb, the second component, and it goes from 0 to 1. So when Xb was 0, the plot for A, if it is a pressure versus Xb plot, so that pressure should be equal to Pa star, because when Xb is 0, Xa is 1, so A is in pure form, so that pressure will be just Pa star. And when Xb was 1, so that means actually it is pure form of X, pure form of B, so there is no A present. So then it should come here. It's basically zero pressure. Now according to Raoult's law, this variation is just a linear variation. So it will just come like this. And for similarly for the other component, which is B, if we ask this question how B varies, or the pressure of B varies, so for Xb equal to 1, it will be the pure form of the B. So it will have some pressures. Let's say the pressure is the Pb star is somewhere here, and then the Raoult's law says that it will again go from 0 to Pb star. So this is a very ideal case. But what you see here, when you vary the mole fraction of carbon disulfide, and if you follow the acetone curve, remember that in that case acetone acts as a solvent, at least in the very dilute case. We'll come to that. And then you see that this actually matches with Raoult's law very nicely, but sooner or later there is a huge deviation. You can see this curve that deviates a lot, and this is the ideal Raoult's law curve. And similarly, if we think in terms of carbon disulfide, you can see that this curve actually starts from here, and then there is a huge deviation. So what we see from the Raoult's law, or the picture of the Raoult's law, is that this is very important. So if you think in terms of the solute, say carbon disulfide, and initially when we are adding the carbon disulfide into acetone, so initially when the mole fraction is very small, so that solution in the sense that it is a solution of carbon disulfide in acetone, where acetone is the solvent, that is a very dilute solution with respect to carbon disulfide. And in the dilute solution limit, actually it works very nicely. So it's a kind of proportionality is maintained. However, the same opposite thing also happens when you think about the other way, meaning you are adding, say, acetone in carbon disulfide. So acetone acts as a solute. So then in this region, when carbon disulfide is in excess, so you see that this actually, I mean, not so well matches with the curve, but it somehow, I mean, matches not so badly also at the very early stage. So the deviation is less there when the acetone is in present. So what it tells us is that when you think about a solute solvent mixture, and when the solute is present in a very small amount, or meaning that solution is very ideal solution, at that condition, you see a nice matching for the solvent but not for the solute. Now that was explained by another scientist, William Henry, and he proposed an alternative law which is known as Henry's law. But Henry's law, let us just try to conceptually analyze what is Henry's law. Now Henry's law says that, or before we discuss about Henry's law, so let us discuss about the solute solvent system. As before, we'll just consider the AB situation. So suppose this is the pure form of A, and then this is the mixture where we just added little bit amount of B, so with respect to B, so this is pure A, and this is A plus little amount of B. By little amount, so which means actually it's a dilute solution of B, which is dissolved, or let us write it as a dilute solution of solute B dissolved in solvent A. Now what Raoult's law says is, for any component we can write XA is nothing but the partial pressure of A into the, or we can write it in this way, PA by PA star. Similarly for XB, Raoult's law also says that the vapor pressure, if we follow the same equation, it will be PA by PB star. But Henry's law, by argument, Henry said that this is very unlikely, because when at the limit of very dilute condition, dilute with respect to, always remember, one component, which is the B component, when B is very less in amount, it is very highly unlikely to consider the vapor pressure, or the vapor pressure of B in this mixture to be equal to the vapor pressure of the pure B, because remember that pure B will be something like this. So this is pure B, and where there are also, it is in equilibrium with its vapor. Here also we have equilibrium with its vapor, and here we have both, but of course the amount of B will be less. Now what Henry's law says is that when you are making an approximation with respect to the solvent for a dilute solution, so then the solvent, which are basically the A in this case, which we denoted as this large circle, they are present in large excess, and they somehow resemble this thing, because if you can see that there are a large number of solvent molecules here, and here actually it is just the pure solvent molecule. So in presence of a trace amount of solute, it doesn't matter. However, from the solute's perspective, if you are thinking that this condition is same as the pure solid, that will be erroneous, very much erroneous, because in the pure B form it is in much excess, whereas in for the dilute solution it is in much less. So Henry said that for solute you cannot use this approximation, and then he just said that for solute it will be something like, you cannot, since you cannot approximate it the ideal case as the PB star, so the pressure, he said, instead of writing it as like this, let us write it in this way, that he said that PB will not be XB into PB star, but it will be XB times some constant, and this constant was an empirical constant which Henry tried to measure from experimental quantities. And what he showed is that for many solutes, he showed that whereas Raoult's law actually tells you that if I change the amount of XB or the mole fraction of XB, then this will be the ideal situation where the final pressure will be nothing but the pressure of vapor pressure of B in its pure form, and the initial pressure will be 0, and then the ideal behavior is something like, the real behavior is something like this. And what Henry's law says is that the initial part, if we draw it more carefully, so suppose it will be something like this, and what Henry said is we can approximate it, the initial part to be equal to a constant, but of course at a very high concentration of the solute, Henry's law will also fail. But Henry's law matches more in a better way than Raoult's law for many solutes, because it just talks about only that part where the solute was in where basically the solvent was in large excess or the solute was in trace amount, which means with respect to B or with respect to one particular component, it was a dilute solution. Now this A and B notations are just purely arbitrary. When you keep on increasing the solute concentration at a very high solute concentration, in this case, if these are two miscible solvents, then in that solution, the second or the earlier the solvent, which is basically A, from its perspective, it's a dilute solution. So always keep that in mind. These are all arbitrary because it's depending on the mole fraction, and when the mole fraction of one component is less, which means the other component is in large excess, then it is a very dilute solution with respect to that particular component. But the situation will be just reversed when you keep on increasing the concentration of that particular component and reach to a situation where it is almost equal to 1. So then the original component, the original solvent, has now become solute. So this is just arbitrary notation. So usually by convention we always say that the B component is the solute and the A is a large excess to begin with, and which will of course be reversed eventually. And in the dilute limit, when B is in much less compared to A, you will see a linearity behavior, but this linearity will not be proportional basically to the PB star. And the physical reason is something like that. When this is a very dilute solution with respect to B, then you see a very large departure from your Henry's from your original Raoult's law. Now, if you can see it here also, now, like for example, when we have this acetone water mixture, when we had carbon disulfide adding in a very little amount, so with respect to carbon dioxide, carbon disulfide, when it was a very trace amount, then the ideal solution will be this part, and you see that in that part actually it deviates very largely. So the approximation that PB is proportional to PB star is wrong. However, PA is proportional to PA star is still correct, because of this picture that we can still approximate that in the solution the vapor pressure of A will be proportional, or the mole fraction will be proportional to the vapor pressure in the pure liquid form. So for acetone, it matches very correctly. So this is all with respect to only Raoult's law is plotted. So where PA is we can write it as XA into PA star. That is more or less valid, but with respect to B, it is very wrong to write as XB into PB star. Similarly, exactly the opposite situation happens. So when you have it here, that when you write it in terms of PA, or A is the solute, as XA into PA star, it is just very wrong because it has a huge departure. However, with respect to A, not A, it will be B. With respect to B, when the B is in large excess, you can actually write XB into PB star. So Henry's law very cleverly poses this entire situation of defining the solute and the solvent in a very different way. And he says that we have to consider only for the dilute solution. Dilute means one component is much less, and when one component is much less, then Raoult's law fails for that component. For the other component, of course, it will be a very good agreement because it acts as a solvent, and the solvent is in large excess, which is equivalent to saying that it is equivalent, it has its properties will be equivalent to the properties of the pure solvent itself. So Henry's law is just trying to understand or reformulate Raoult's law in a newer way, in some sense. And then this is a real curve experimental data for two solvents, acetone and chloroform, and also you can see there are other solvents also is here, like acetic acid and chloroform. Now you can see that these dotted lines are the Henry's law. These dotted lines and you can see that this is basically Raoult's law. So both actually are linear variation, and Henry's law were formulated only for dilute solution. So just to summarize, for Raoult's law, it whatever we got is this relationship that the mole fraction will be equal to the partial pressure divided by the total pressure. Instead of the total pressure, we are writing it as equivalent to the pressure of the component when the component is in pure form. That will hold only for some solvents. Of course, reality is very different, and those solvents of those systems we call as ideal systems, and solution we call as ideal solution. Now within the ideal solution, Henry's law says that from solutes perspective, solute means the component which is very less, the Raoult's law fails because of the situation that the solute is in very less amount, and then you see a large departure. Now here are some experimental data again. Now coming back to the last part of this section on mixtures. So we have so far discussed about the thermodynamics of mixture, and then we discussed about how Gibbs free energy changes with respect to addition of one particular component, keeping pressure, temperature, and all other components constant or unchanged. And then we discussed how basically the pressure of a particular component in a two-component system changes by addition of one particular component, and we discussed the Raoult's law and Henry's law. Henry's law actually talks about the limiting case of Raoult's law, how to modify it with respect to the solute which is present in trace amount or in less quantity compared to the other component. And now the last thing which we are going to discuss is some phenomena or some collection of phenomena which are known as colligative properties. Now this name colligative means actually it depends on the collection, meaning it's a collection of phenomena we are about to discuss. Now, suppose it's when we start to begin with, suppose you have a pure liquid, say pure water, and you add some salt. Now the question we are asking, we know that pure water under 1 atmosphere freezes at 0 degrees centigrade or to 73 Kelvin. The question is whether if we when you add a little bit salt to it, how the freezing point changes. And we know that of course freezing point changes because salt water freezes at a much lower temperature than the freezing point of water, which is 0 degrees centigrade. Now the question is, how does it happen? Now you can easily think about it in terms of, say, the chemical potential, the equation for the chemical potential. So one way to quickly understand is that suppose when we talked about it, that mu versus T curve, if you remember, we discussed it when we were discussing the phase transition, and this was the first thing we discussed, that how the Gibbs free energy varies with temperature, and we said that for solids the variation is much less, and then for liquids there will be some variation, and for gas there will be a much more variation. So here, where we have a phase transition from solid to liquid, so this is a solid region, this is liquid region, so that we called as the melting point or the freezing point equivalently, and similarly this is nothing but the boiling point. So this region is the vapor region. Now suppose we are adding some solute in that liquid. So what will happen is that now the chemical potential, initially the chemical potential of the liquid was basically pure liquid, will be nothing but equal to the mu a star, because the equation is mu a is equal to mu a star plus RT ln XA. If it is in pure form, then XA is equal to 1, which means mu a is equal to mu a star. With addition of a pinch of salt or so, now the XA will change, it will drop from 1, which means this quantity will be negative, which means actually mu a will be less than mu a star. So if this curve for the liquid is in for a liquid which is in pure form, in the mixture we'll have a new curve for the liquid which will lie below to this curve, because it is now less. So that since the chemical potential is less, you'll have a curve like this. So what you see here is that now this curve actually crosses the solid curve, which means the freezing point now is here after addition of the salt. So we see here that we have a freezing point depression. Depression means actually it is lowering down, it has been lowered down. So this phenomena is called as freezing point depression. Similarly, if you follow these two curves, now this is for the mixture, remember this is for the pure form and this is for the mixture, and now they cross here with the vapor curve. So the boiling point, unlike the freezing point, is actually enhanced or increases, so or it is elevated. So we call it as boiling point elevation. So it is just like opposite to depression in the freezing point. Now you might ask a question that, well, what about the solid curve? Because we are only considering the change in the chemical potential of the liquid. We did not consider the solid, how it behaves from the pure or in the mixture. Now here, the assumption is that when the liquid forms the solid, the solute separates out. Suppose when you add some salt to the water, then the assumption here is that when solid ice is forming, it is a pure solid ice. Or when water is vaporizing to a water vapor, it's a pure water vapor. So those two curves for solid and the vapor curve, those are not the chemical potential for those two curves are not changed. Only it is shown in the solution form, which is in the liquid form. So only in the liquid state the solution exists, and the chemical potential of the solute, the chemical potential of the solvent in this case, which is the pure, which was pure liquid, and when we added the solute, it becomes a solvent, and then that solvent is actually suppressed in presence of a solute. But the solid and the vapor, their chemical potential remains unchanged, which means the solute is a non-volatile solute, which also does not freezes along with the liquid, because the solid, suppose the solute freezing temperature is, it basically separates out, and that is the assumption here. But you may encounter some instances where the solute actually freezes along with the solvent, and then this approximation or the way you have drawn the curves will not be correct, because then the solid also will go a little bit down, okay, because the chemical potential should change, because Xa is a fraction, so should be the ln Xa should be negative, but we are not considering this thing here. Now think about it, just like we discussed about how the freezing point is changing or the boiling point is elevated, we can actually discuss the thermodynamics of these processes in much more detail. Now let us start with the elevation of the boiling point. Now what is boiling? Now if you ask this question, think about it like we have a solvent here, and then it is always in equilibrium with its vapor. So suppose I write it as A, liquid, A, gas, and when boiling happens, what it means is that the chemical potential of A in the gas phase must be equal to the chemical potential of the liquid itself, because at that temperature, which is known as the boiling temperature, and also at that particular pressure. Now if the chemical potentials are equal, then it's basically the condition for boiling, so the liquid is in equilibrium with the vapor and it starts boiling. And we discussed it in various contexts actually. If you remember that when we discussed the Amagat's curve or the Andrews curve, not the Amagat's curve. So you showed that this nice pressure volume curve, where we discussed that over a large range of volume, because the volume should change, pressure is kept constant. You see here that the pressure is kept constant, and this is also an isotherm, which means temperature is also constant. And at a particular temperature, if you just keep on increasing the pressure, you can achieve boiling also. Or for a fixed pressure, you can think of, for a particular temperature, will have a boiling temperature. So for water, it is say 1 atmospheric pressure, it corresponds to the 100 degrees centigrade. Now when boiling happens, the volume of course changes, but the thing is that the liquid is now in equilibrium with the vapor. So this is the liquid and this is the vapor. We already discussed it. So if we start from that, and suppose we have a second component now, which is B here, which is a solute, say some salt, we add it into water, and then what will happen that when the when the boiling we are considering, it is the boiling of water, not boiling of the salt. It's a boiling of the water only. So this condition still holds. However, the mu A of the liquid will not be the mu A of the pure liquid, because now the mu A has to be replaced for the liquid state by the partial quantities. But for the gas, we can still say, or the vapor phase, it is basically the mu A star or the pure form, because in the gas phase there is no B, because we just added a salt which does not come into the gas phase. But for the liquid phase, instead of mu A, we should write mu A star liquid plus RT ln. So basically the way we are writing it is we can write it as XA. Now, because PA by PA star we approximated, PA by P0 we approximated as XA. Now what we are seeing, what we just saw here is that we can take the difference, which is basically the, if we write this in terms of ln XA, we'll get it will be 1 over RT into mu A star of the gas minus mu A star for the liquid. Now this is basically the difference in the chemical potential in the vapor phase minus the gas phase, which means it is the associated free energy change per mole, because it's mu. So we can write it as the associated delta G per mole, and this is a vaporization process, so this is delta vaporization of G, and this quantity we want to estimate. Now remember that instead of writing how the ln XA is changing, we could also, we are trying to figure out a relationship between how much XB we can add so that we see a change in the boiling point, something like the curve we wrote. So we want to get an expression for this quantity as a function of the solute added, which is the XB here. So XB you can easily write as 1 minus XA at any point. So this XA we just have to replace by 1 minus XB we have to replace by 1 minus XA, or the other way, XA can be replaced as 1 minus XB. But the question is, how will you get the delta T equation? Now if you remember that we used a Gibbs-Duhem equation where we talked about the variation of delta G with respect to temperature, and that was connected to the enthalpy. And since this boiling is happening at constant pressure, and also the temperature is also constant, from this curve you can easily see that from Andrews curve, so we can actually write, instead of the delta G, a relevant quantity will be how much heat is supplied, and heat transferred at constant pressure is nothing but enthalpy. And then you can always argue that I can use the Gibbs-Duhem equation to get this. So Gibbs-Duhem equation is nothing but the derivative of delta G with respect to temperature at constant pressure. So on left hand side I have to take d ln XA dt. I'm not writing the del notation because the pressure is always constant, it is already there. So that will be 1 over RT, and then we have we can write it as d dt, sorry, this is capital T, of delta G, this is delta of vaporization of G divided by T. So this T actually got inside, so that is nothing but del H by RT square with a negative sign. So it will be 1 over RT square and the numerator is nothing but the associated change in enthalpy of fusion. Now we can integrate this equation and see how it appears. So you can easily see that if we integrate it, so we'll take the temperature on the other side. So we'll get ln d ln xa integrated will be equal to minus 1 over r integral of delta fusion h divided by t square dt. Now you can easily integrate it. I'll just use this space. And the integration or the integrand will be, if we take the lower limit of the integration to be 0, or when we have ln xa is to be 0, so then we are saying that ln xa to be 0 means, think about it, that xa must be equal to 1, which is the liquid in the pure form. So then the T is nothing but the T star, or the boiling, the pure liquid's boiling point, and the upper limit, let's call it as T, and let's call it as ln xa. So we have ln xa, which we can write as ln 1 minus xb, and the right hand side will become minus 1 over r. So the integration of 1 over t square is minus 1 over t, so that minus gets cancelled with this minus, and if we just calculate the limits, it will be 1 over t minus 1 over t star. So what we'll get is delta H vaporization by R, and there will be a delta H vaporization by R, and then we can write it as T minus T star divided by T into T star with a negative sign, and that we can further approximate as this T into T star we can approximate as T star squared. So we can write it as delta vaporization divided by R into delta T, which is the elevation in the boiling point, divided by T star squared. This is just an approximation. So what we just saw is that, so there will be a negative sign here somewhere. It is 1 over T minus 1 over T star. So there will be, I guess, a negative sign here. So what we just discussed is that we have gave a formalism to understand the elevation of boiling point. Similarly, you can use the same formalism to understand the depression of freezing point. When you discuss the freezing point depression, instead of the delta H vaporization, we write it as delta H of fusion, but the maths is exactly the same. Now, alternatively, sometimes you write it as, instead of this delta, the expression for delta T is sometimes written as, the expression what we got is R by delta vaporization H into ln 1 minus xb, and times we have T star squared, and sometimes it is basically it is proportional to, as we can see, it is proportional to xb, and then you can just manipulate all these terms. So ln 1 minus xb you can approximate to be minus xb, and then you can further write it as R divided by delta vaporization H, you can write as T star squared into xb. So this is some constant into xb, and you can further approximate that xb is proportional to the molality of b, and then you can get it some other constant, which is basically this constant multiplied by some other constant, which is the proportionality constant between mole fraction and the molality, and then you can write it in terms of the molality, and you can, in a shorthand notation, you can actually write it as kb into b, where b is the molality of xb, molality of component capital B, and k suffix b is nothing but the sometimes it is called as the boiling point elevation constant, and similarly for freezing point we write it as k suffix f into b. So you can connect it to molality. So the delta T ultimately can be written as a constant, which is basically a rearrangement of all the constants times the molality. So this equation shows how one can connect the amount of B at the mole fraction of B, which is xB, or equivalently the molality of the B, to the depression of freezing point or the elevation of the boiling point. We derived it for the elevation of the boiling point, but the similar mathematics also holds for the depression of the freezing point. So let me now summarize what we discussed in this lecture. So we started with the partial molar volume, and we talked about how we can use these partial molar quantities. One, we discussed about the partial molar volume, and then we switched to the partial molar free energy, and then we discussed that this free energy change, which is basically the chemical potential, is a very general concept, and it is not that you have to always use or always express it in terms of Gibbs free energy. You could also express it in many other things like the internal energy, enthalpy, and so on. So mu I is a very general thing, and then we derived expression for mu I. First we talked about the gaseous mixtures. If we have two gases and we are mixing it, and then we calculated the delta G of the process is mixing, and we found it is negative. So they mix, two gases actually mix spontaneously. And then we talked about what will be the similar quantities for two liquids. And in this case, we showed that we have a general formalism, which is the Raoult's law. And then only for the, and this these solutions which behave Raoult's law or Henry's law are called as ideal solutions. And for this ideal solution, Raoult's law does not apply for the dilute condition, dilute with respect to a particular component, and that component doesn't obey Raoult's law, and for that there is Henry's law, which is for the dilute case. So it is for ideal dilute solution. And then we discussed the molecular origin for Raoult's law and Henry's law, why it is valid in one limit and why the other one is valid in the other limit. We talked about the solid-solvent interactions. And then we talked about, in the last part very briefly, what is known as colligative properties. So there we talked about if we add a pinch of salt in water, why the freezing point is depressed or the boiling point is elevated. When we found a relationship between this depression or enhancement in the boiling point or freezing point, or vice versa, it's depression of freezing point and elevation of boiling point, and connecting to the amount of the solute added to it, or the mole fraction of the solute added, or equivalently the molality of the solute which is added to it. And we could also discuss few other things like under colligative properties, like one of the interesting thing is how osmosis happens, because if you remember that osmosis of a solution where we have a semi-permeable membrane and only the solvent is transparent to it or permeable to it, then we have a interesting phenomena which is osmosis, which we could also explain in terms of the diffusion of the solvent. Now we'll have a problem set, and where we'll ask you to derive the thermodynamics, or try to learn the thermodynamics of osmosis through this through the concept which we just developed. So in the next lecture, we'll be discussing about chemical equilibrium. So we'll talk about chemical reactions and what are the conditions for equilibrium, and how one can actually enhance the amount of one particular substance or say the product at equilibrium by just playing some tricks. But we won't be discussing any rate of the process, how quickly the equilibrium is achieved at this point. And in the following lecture, we'll be discussing about electrochemistry, or the equilibrium electrochemistry. What happens, what are the thermodynamics of electrochemical cells? Thank you.